Hey guys, here we are in section 5.5. We're going to be talking about roots of real numbers. So let's go ahead and get started. Our vocabulary consists of three phrases: square root, which you should be familiar with, right? So if I told you x squared is equal to 25, we can take the square root of both sides. And when we do that, we get that x is equal to, we got to consider positive or negative 25 or plus or minus 5. That's the idea when we take the square root, right? The nth root, well, here's the thing. The square root, we don't usually write this. We just usually use the symbol for the square root. But there's like a low-key secret too, to say I'm looking for two numbers that multiply to give me this 25. Then the same number multiplied twice, rather. Same thing with the nth root. The nth root is kind of the idea where any number can be out here, all right? So the nth root looks like this. The nth root of a would be like this. For example, I can have the third root of 8. So that says some number multiplied by itself 3 times or to the third power that equals 8. And we all know that that answer is 2. I could also have like the, fifth root of 32, which would imply that there's a number that I can multiply 5 times to get 32, which also happens to be 2. So we call this idea of having an index number out here, we call it the nth root. I hope that makes sense. Hopefully the examples will help out. When we talk about the principal root, specifically, if I'm talking about the principal square root, let's say, the square root of 25 has a principal square root of 5. What this means is I'm not considering the plus or minus. I'm just considering the principal square root, the particular square root, which is 5. And with our vocabulary discussed, let's move on to some examples. So here, when we take the square root, they said, analyze, tell us what the plus or minus the square root of this is. Well, the plus or minus is going to stay, but the square root of 25 is 5. And the square root of x to the fourth power will be x squared. So the answer here will be plus or minus 5x squared. Similarly, we're going to come over here and take the square root of this thing. Notice, I'm going to highlight this. This green blob is to the 8th power, right? This green blob is being to the 8th power. So I'm taking the square root of this thing to the 8th power, which is going to be, well, the 4th power, right? So I'm going to get this thing, which happens to be y squared plus 2, to the 4th power, and I shouldn't forget my negative that comes along. Over here, the 5th root of this business, okay, so now we got to think. The 5th root means that there's a number that I can multiply 5 times in order to get the number here, and I'm looking for that. So in this case, we actually just did this. We know that the 5th root of 32 is going to be 2. And let's consider what the 5th root of x to the 15th would be. And it might be kind of hard to think about, but basically what you're going to be doing is taking this 15 and dividing by 5. Because think about it. If I have, let me go back underneath the radical, and taking the 5th root, the 32 came out as a 2, so I'm not going to deal with that anymore. What can I multiply 5 times in order to get x to the 15th? And it will be x to the 3rd. You see my vision? So we have 5x to the thirds, right? And basically, if I took 15 and divided it by 5, I would have gotten x to the third. So once I've got the 5x to the third, I know the 5 things that multiply to give me x to the 15th, and that's x to the third. So now x to the third can come out, or rather x to the 15th, 5th root of x to the 15th comes out as x to the third. And let me write that over here, x to the third. It's getting a little crowded. So we have 2x to the 3rd power, and we're now dealing with the 5th root of, we've dealt with this, y to the 20th. And if you think about the analogous situation, what did I say last time? Take that 15 divided by 5 and you get 3. Take this 20 divided by 5 and you get 4. So this whole thing, I know I'm not making this pretty, but that's okay. You guys can follow along even with the not too pretty, will become y to the 4th. And I can explain this in greater detail if you'd like. If you're like, I'm not sure, this looks like witchcraft, lady, I don't know what's happening, I can, write out 20 y's, right? Imagine me writing out 20 y's and then grouping them in groups of 5, right? Which is basically taking 20 divided by 5. Each of those would be like a y to the 4th, right? So what 5 things multiply to give me y to the 20th, y to the 4th? And if I'm taking the 5th root of it, I only need the 1y to the 4th. Are you with me? I hope that made somebody happy and it clarified something. And if it didn't, if it only made you sad, talk to me. Let's see if we can get to the bottom of your sadness and make things make sense. Now, technically, right now, we're at a place where we say, oh, we can't do it. This is too hard. Oh, no. Because there is no value in the real world system where the square root of 9, where I can take, you remember this is really the square root of 9 or the second root of 9. There is no value where I can get two numbers that are the same that multiply to give me negative 9. We will kind of hold this off in our minds as right now no real solution, okay? But we're going to be talking about imaginary numbers quite soon, so we'll be able to think through the idea of how to take the square root or what we would do to represent the square root of a negative number. All right, so let's go ahead and think about absolute values in these situations. Let me explain something real quick to you. So it's not even real quick, it just makes sense. Let's imagine if I took negative 3. That's the number I'm starting off with. So let's say x equals negative 3. If I take negative 3 and I say, let's take negative 3 and square it, or square x, right? And then I take the square root of that x, what am I going to get back? That's the question that we're going to ask ourselves in thinking that x is negative 3. Well, if I were to take x square it and negative 3 and square it, I get 9. And when I take the square root of 9, I get the principal square root, which is 3, or I get 3. I don't get negative 3. So technically, do you see what just happened there? By squaring that negative number and then taking the square root of it, I kind of eliminated the negativity of the original number. I didn't get x back is what I'm saying. I got something else. And so what this law and what this idea is coming up with here is that when we do that, when we take any old x squared and we take the square root of it, we don't actually get x back, we get the absolute value of x. Think about that for a second. Now, what I need you to know as you're thinking through that is that this is only a concern when this index number, right, this root, the nth root, is an even nth root. When n is even, this is the only time to be concerned about it. And if you give yourself a couple of examples, you'll see that that's the case. So notice this example, when we talk about simplifying using absolute value, will only contain situations where these roots are positive, or even rather, because even roots are always going to have a positive answer. You can't really have a negative answer for an even root. Now this is different. I know this is a little slick. This is different than when I say x squared is equal to 25. Therefore, the square root is plus or minus the square root of 25. Look, I had to add the positive and negative in order for us to consider the positive 5 or the negative 5. I had to add that with the knowledge of what x squared could be. But when I just take the square root of 25, I'm just getting the principal square root, which is going to be that positive value. And similarly, when I take the even root of any number, I'm always going to get a positive answer. But since I don't know what I originally started off with, I got to throw in that absolute value. So it looks like, remember how I said you can just divide the index number into this exponent? So you're looking at this and you're like, oh, x to the x to the 8th power, then you take the 8th root is just going to get you x back. Not necessarily. Not if x were negative. So I got to throw that absolute value in there. Over here, same thing. The 4th root of this thing of 81 times the quantity of 8 plus 1 quantity squared. Well, let's deal with the 81 first. 81 is 3 squared times 3 squared, which is really 3 to the 4th power. So the 4th root of 81 is going to give me a straight up 3. Now the fourth root of a plus 1 to the 12th power. Remember, I'm just looking at this as a blob. This is a thing. I'm not worried about it. I'm just looking at, is it something to the fourth power? The fourth root of that is going to be, take the 12 divided by 4. You're going to get 3. So you end up with a plus 1 to the third power. Now here's why we got to put absolute values in this thing. Remember, when I take the even root, I'm always going to have a positive answer. That's just what it's going to be. However, a plus 1 to the third power, if a was like a -6, this is going to be a -5. -5 to the negative third power is actually a negative number. Multiply that by the +3, this thing negative. And remember, I said every time we have this even index, it's got to be positive. So I've got to throw absolute values around the part that could be negative. It's kind of weird. I'm going to go back real quick because we had an example where I did not say anything about that. Let me see, which one was it? This one here. Notice I took the square root of something, and I know that there's a negative here, but let's even think like the negative's not there. I did not have to put absolute value here. And the reason why is, first of all, the y squared is going to cancel out the negativity. But also to the fourth power, if this was a negative term, the fact that it ended up to the fourth power, I don't have to worry about it. So the square root, the fact that the square root has to come out with an originally positive answer would still be intact. I know that was over explaining. I get it. Let me know if I'm making you uncomfortable with this stuff. Let's look at something else. Example 3 is our last. The time t seconds that it takes for a pendulum to make a complete swing back and forth is given by this formula. Whenever you see stuff like this that you're like, man, I don't know what this is, pendulum swinging, yeah, your goal in math is to find the math in it and see how you can break this thing down. So what I'm looking for, as soon as I see a formula like this, I am looking to see what each of these things refer to. And I'm going to write myself notes if it helps me. So I got to figure out what T is, I got to figure out what L is, and I got to figure out what G, all of these things stand for in order for me to do the problem. So they told me right now where L is the length of the pendulum in feet, and G is the acceleration due to gravity. And as I search around, I see T was given to us in the beginning. T, the time T in seconds, it takes the pendulum to swing back and forth. All right. So now that I have this information, I kind of grade it out so I can write over top of these things. So what I have is find the value of T. That's what we want to do. For a 3-foot long pendulum, where did they give me length? Length of the pendulum. So I'm going to put a 3 right in here. For a 3-foot long pendulum, and we need to figure out what the acceleration due to gravity is, and that's 32 feet per second. That's like a constant. So I put that there. So I need to calculate this, and all of this, these are just regular numbers. So 2 pi and all that stuff. So T is going to equal all of this stuff, and this is kind of straightforward. I'm just going to plug a lot of this into my calculator. And when I plug it into my calculator, we're going to get, just being lazy, using the textbook, 1.92 as the value, which tells us that it takes the pendulum about 1.92 seconds to make a complete swing. With that in mind, I am going to let you go. I hope that we can talk about any questions or concerns you have. This word problem didn't really deal with some of the things that we dealt with up here. It just had a radical in it. So it wasn't the greatest word problem in the world. But let me know if you have trouble with word problems or if you have any trouble with the concepts that we've been talking about. Let's get together. Let's talk. We could do something and work something out. Listen, take it easy. I hope you have a good day. Bye-bye.